Let's start by setting up the ball movement and collision detection. We'll make a new scene, and for the root node, we'll choose character body 2D, just as we've chosen in the past. The reason is that we're not using forces directly to move the ball. Again, we need to pick a collision shape as the child. Unlike before though, we're going to choose a circle shape. Let's set the radius to 12 pixels. And we can zoom in to see what it looks like. We will still need a visualization though, so let's add a color rect as the child. So this color rect does not match the shape of our collision shape circle. To make our color rect match that shape, we'll need to apply a custom fragment shader. To explain fragment shaders, let's first imagine that we have an array of colors, and this array of colors represents every single pixel on the screen. Let's say that we wanted to make every single pixel blue. How would we do that? Well, we would use a for loop, and we would loop over this array. We'd go from I in range 0 up to the size of that array. And then what we would do, it was set colors at I equal to color dot blue. That's how we would do it normal programming style. A shader though is very, very parallelized. On the CPU, we're sequential. On the GPU, with a shader, we're in parallel. And the part that gets executed in parallel is this inner body of the for loop. So let's see what this looks like in Godot. I'm going to go back onto this color rect. I'm going to expand the material, and I'm going to make a new shader material. For the shader, I'm going to choose a new shader. Let's also create a directory for shaders. And then I can just rename it to ball.gdshader. And I'm going to create it. And I can click this, and then we get a brand new shader editor that opens up down here in the editor. What I'm going to do is delete vertex and light. You don't really need those right now, or the comments. To translate that CPU code above into GPU code, what we can do is say color equals vector4. This vector4 is going to hold the RGBA values of the color. If we wanted to make this blue, then we would set the R to 0, G to 0, B to 1, and alpha to 1, just so it's not transparent. And there you go, we have a blue rectangle. And so you can see that what the shader is doing is taking that body of the for loop and basically putting it here. So we don't really need this right now. We can go back into our view like this. So this is great for just solid colors, but of course we're trying to make a circle here. So how do we do that? Well, before we can get into that, let's first explain what a UV coordinate is. UV coordinates go from 0 to 1 across this color rect on the x-axis, and 0 to 1 down across the y-axis of this color rectangle. We can use that to figure out where we are in the image. Let's visualize this. Rather than displaying solid blue color here, let's instead, on the red channel, display the x-coordinate of our UV space. And so we can very clearly see that the x-coordinate of the UV space increases from 0 to 1. If I were to swap this for the value of y, we can see that y increases from 0 to 1 as we go down here. Let's try something now. We know that inside of the shader, the UV coordinate is a vector 2, because it has the x and the y coordinates. What if we were to get the length of that vector? Let's see. I'm going to make a float called len for length. I'm going to set it equal to the length of our current UV coordinate. And rather than putting uv.y here, I'm going to put len for length. This might look confusing, but if you zoom in, you can actually see the beginnings of a circle, like one quadrant of that circle. We can use this to make a full circle inside of this rectangle. Let's see how. The UV coordinate space, as explained before, is from 0 to 1, 0 to 1 down. What if we were able to shift it over to the center? Well, we can do that. If I make a new vector 2 called centered UVs, I can set this equal to UV times 2 minus 1. What this is doing is saying, okay, 0 to 1, actually double it, make it 0 to 2, but then just go ahead and shift it back into the center. And rather than grabbing the UVs here, I'm going to grab the centered UVs. And now we can see we have a circle centered in the center of this image. Let's do another experiment. What if I were to subtract away 0.2 off of the length? We can see that it gets a little bit darker, but what are we really doing here? This is actually a very basic signed distance field. It's called a signed distance field because it's a bunch of distances, but some of them can actually be negative. We're going to interpret the negative parts as being inside of the circle and the positive parts as being outside of the circle. To really get a handle of how to visualize this, we're going to use the step function. The step function takes x and y, and what it does, it says, can I step over the value of x using y? If I can, then I'm going to return value of 1. Otherwise, I'll return the value of 0. Let's do an example to visualize this. I'm going to comment this out, and I'm going to replace it with this assigning color to a vector 4, and I'm going to replace the red channel with a call to the step function, and I'm going to say, can I step over a point 2 using uv.x? And I'll fill in the rest with, doesn't really matter. And so we're saying, can I step over point 2? Yes. So then it'll be a value of 1 in the red channel. Otherwise it'll be 0. So now we can use this to display the circle. I'm going to delete this line. I'm going to bring this back here. And I'm going to make another variable called circle. And this is going to be equal to the step over 0 using length. This says, can the length of our UV coordinate space centered here step over 0? And if it can, that means we get a value of 1. So what would happen if I put this here into circle? You can see that the outer part is 1 where the inner part is 0. We're going to want to invert that using 1.0 minus the step function. And that'll properly display the circle as positive inside the circle and negative outside of the circle. And we've done that using the step function. What if we want to change the color of the circle though? To do that, we can use the mix function. Mix is going to mix between two colors from A to B by a float t. I'll explain that with an example. I'm going to get rid of color here, and I'm going to say that color is equal to mix. Let's say I want to mix from, let's say, red, 1001, over to, let's say, white, 1111, and I want to mix between those using uv.x. And there you go. I'm taking the UVX coordinate to mix some red smoothly over to white. So let's use that to change the color of the circle. I'm going to get rid of that. I'm going to bring this back. But then I'm going to replace this with a call to mix. And I'm going to mix from, let's say, a vector 4 filled with zeros, so basically just a clear, transparent color. I'm going to mix over to our target color, let's say blue. So 0, 0, 1, 0. And I'm going to mix using our circle variable. Oh, and that didn't work because, that's a good point, the alpha channel is 0. Make sure that's 1. And there you go. There's our circle inside of this color rect, just like we were trying to do. So this is good. However, all of our crucial variables that we'd want to tweak are buried in the shader code. It would be nice if we could just tweak these outside of the shader, so we could easily change the radius or the color of the circle. We can accomplish that using uniforms. And a uniform is a variable that is the same across all of the fragments. So let's make one for the radius. I'm going to say uniform float radius. I'm going to set it equal to 0.2. And we can see that a cool thing happens over in shader parameters that gets exposed to us here. So I can change the radius. Of course, it doesn't do anything yet. So we'll just replace that 0.2 with our radius uniform. And now we have full control over the radius, which is pretty cool. It would also be cool if we can change the color of the circle. So we'll just make a new uniform of vector 4. We'll set it equal to, we'll call it ball color. And so Godot will expose it to us, but not in the way that we want. It exposes it to us just as a vector 4. So we can give this variable an annotation to give Godot a hint about how we want this variable to look. So I'm going to do source color here. Now the inspector looks much nicer with a color picker. And then it's just a matter of replacing this with ball color. And there you go. Now we can control the color very easily of this circle. Say it's purple like that or something like that. And now we can drag this over our collision shape. Like so. We can change the radius just a little bit to cover it nicely. And there we have it, a nice circle. Now we can start scripting the ball's movement and collisions. Oh, let's actually rename this to ball before we continue. And we can add a script. I'm going to put this into the scripts folder and call it ball. And now that we're here, I'm going to delete all of our templated code here. So let's start simple and override the physics process as we've done in the past. We're going to want the ball to move with some velocity. So we'll use move and collide again. And for the motion, we'll pick ball velocity times delta time. Ball velocity doesn't exist yet, so let's make a variable for that. And we can assign it to a vector 2. Let's say 400 to the right for now. Next, let's go back into our main Pong scene and drag our ball scene into the court, like so. Slide it up like that. And if I hit play, the ball does move, but it doesn't bounce. But that's okay, because we haven't told it to yet. So let's go back into our script. Move and collide is going to return a kinematic collision 2D object if there is a collision. If there's no collision, then it's going to return null. So we're going to set the collision of type kinematic collision 2D equal to this result of calling move and collide. If there's a collision, we need to bounce this ball somehow. So how do we do that? Well, we're going to use something called vector reflection. This shader simulates what a vector reflection looks like. In our example, let's consider the white arrow to be our ball's velocity, the pink arrow the surface normal, and the yellow vector the reflection vector. The surface normal is the vector that's perpendicular to the surface we've collided with. So imagine a wall right here. This pink arrow would be the normal of that wall. So we can see that the ball would bounce against this wall and the velocity has to get reflected. And this orange vector represents what that reflection vector will look like. To see more examples, we can see what happens when we change the angle of our velocity. Or increase our speed. Now let's go back to our script and use what we've learned here. We're going to adjust our ball's velocity when there's a collision. We're going to do that by calling ball velocity.bounce. And we're going to bounce against the collision get normal. I'm using bounce and not reflect here because bounce accepts a surface normal, whereas reflect is accepting a line. They'll do the same thing, it's just a different way to call them. So now that that's happened, let's hit play and see what happens. Nice, the ball is bouncing off the paddles. So this works, but it's pretty easy to play and there's no challenge. So we can fix that by having the ball launch at a random angle. Let's override ready here. And ready is called at the beginning of the game. And the first thing we want to do is pick a random angle. However, we don't want to pick any random angle because if we pick something too steep, the ball's just going to bounce up and down the whole time, which we don't want that. So what we can do instead is pick some angles that are within a certain range. What I mean by that is let's make a variable called random angle. We'll assign it to randf range, and we want it to go from negative pi over 4 all the way up to pi over 4. This is going to launch the ball at a random angle on the right side, but we also want it to be able to launch to the left. To do that, let's say if random I mod 2 is equal to 0. What am I saying here? This is saying do rand I, which is giving me a random number from 0 all the way up to the max value an integer could be, and mod it by 2. And this is going to give me a number between 0 and 1. So this is basically a coin flip. So if that coin flip happens to land on 0, let's go the other way instead. The way I can do that is I can just add pi to this angle. That'll flip it around. Now that we have our angle, we can go ahead and set our ball velocity. We can do that by assigning it to a new vector 2, where the x is going to be the cosine of a random angle, and y is going to be the sine of a random angle. And then we can just scale this by speed. Of course, we don't have a speed variable yet, so let's go ahead and make one, and let's set it to 700. And there we go. So now that we have that, let's run the game and see what happens. Nice. We have a random angle that the ball is chosen to launch at. One quality of life thing we want to do before we leave is let's have the ball launch at a slower speed at the beginning of the game, but then after any collision, resume back up to the full speed. The reason we're going to do this is so it's not too jarring when you're first starting the game. So let's make a variable called initial speed. Then we can go ahead and set it to 400. Now, at the beginning of the game, launch at the initial speed instead of the full speed. When there's a collision, we'll correct the ball's velocity. We'll set the ball velocity equal to the ball velocity dot normalized, making it have a length of 1, and then we'll stretch it all the way up to the full speed. Let's see what happens now. There you go. Nice slow speed, and then it speeds up. Very nice. So this is definitely a great start, but there's still much more to do in terms of making this a challenging experience. As right now the ball is just going to bounce at the same angle, regardless of where it hits the paddle. That makes sense from a physics perspective, but from a fun and challenging experience perspective, it doesn't make sense. So next time we're going to be looking at how we can address that.